All right, Taylor and Maclaurin series. As you can see from the screen here, this is going to be a little bit of an info dump at the beginning, but let's try and take a deep breath, go through it together, understand what the point of this is before we jump into the calculations. It's really important. So what I'm trying to make a point about here is that at this point so far, whenever we're trying to represent a function as a series, we've always used this geometric series of ratio x in one way or another. But in some cases, this is not even possible. If you remember how I did the power series for arctangent x, what I did was I took its derivative, and that was 1 over 1 plus x squared. And then I wrote this as 1 minus x squared. And then I sort of matched this with a power series of geometric series of ratio negative x squared. Now, this was really lucky of me that when I derived arctangent, I got something that resembled the sum of a geometric series, and that's not always the case. For example, what about the sine function? If I have f of x equal to sine x, I can take as many derivatives of it as I want, or as many integrals of it as I want. I'll never get something that's close to 1 over 1 minus x. So how do I go about it then, right? And the key question here, is that even possible? Is it even possible for me to find a power series representation for the sine function, or say the cosine function? Because if it's not possible, then a lot of the applications that we talk about aren't really interesting and helpful. They're really limited, right? So let's talk about when this is possible. So when it's possible, we're going to say that the function is analytic. So the function is going to be said to be analytic at the point A if we can write f as a power series that converges, of course, right? And the power series has a positive radius of convergence. So this needs to be in the interval a minus r, a plus r, with r positive. So if that's possible to do, for some a, as long as for some r, as long as r isn't 0, right, then we say that the function is analytic at a. So a could be 1, and if we can find a power series that at 1, they're at 1, then the function is analytic at 1. Maybe at 1.5 you find another power series, at 3, at 7, and at 17, at pi. So the collection of the points at which the function is analytic matters, right? And again, just remember us saying that the function is analytic just means it's possible to write it as a power series. So some of the functions that we know, some functions are going to be able to be represented this way, some won't be able to be represented this way. But the great news is that almost all functions that we work with in calculus are analytic. So this is a theorem. Again, this needs to be proved. I'm not going to prove it to you. It's not very interesting, I don't think. But the proof here is, I guess the takeaway or the conclusion of the theorem here is that if you have a polynomial function, you can represent it as a power series. If you have a rational function, an exponential, a logarithmic, a trigonometric, or an inverse trigonometric function, all of these functions can be represented as power series in all points of their domains. So if you get something like 1 over 1 minus x, of course you can't write this as a power series centered at 1, because of course 1 is not in the domain, so this is rational, so this is not possible. But everywhere except for 1, it is possible. This is what this theorem is saying, okay? The theorem is saying that it is possible. It's possible, right? So how, right, is the next question. How do we do it? proving that this is possible is already kind of concerning. It takes a little bit of time. How to do it, though, is not so complicated. So I'm going to go over how to do it. So let's assume that we already have it. Assume that you already have it. Assume you already have it. So you can write f of x as being, c0 plus c1 x minus a, just plugging in n as we go. And you can see that I'm just plugging in n, so the n follows the power of x minus a here. Okay, how do I possibly find this thing? It seems difficult. Find each c, right? To find the series, I only need to find the c's. So it seems difficult at first, but you can see all of it by just plugging in a. Right? What do you get? This is c0 plus x minus a is going to be 0. And this is going to be 0. It's going to be 0 cubed, 0 squared, and so on. So c0 will be f of a. Okay, so that's great. That's a great start. Next, how do I find c1? I look from this expression on the top here. This one. I'm going to be using this. I'll take its derivative. So f prime of x. So the c0 is going to go away because it's a constant. And now the derivative of this is going to be c1. This is x to the power of 1. So, and the derivative of this will be 2c2 x minus a. And the derivative of this will be 3c3 x minus a to the power 2. And then I can plug in 0 again, or plug in a in this case. F prime of a will be c1 plus, and now this is going to be 0, and 0, and 0. So that means f prime of a is c1. Great. Awesome. So let me actually write it backwards like I did in the previous box, because I'm trying to find the c's, right? So you can see already some sort of pattern emerging. How do I find c0? I derive f0 times, plug in a. How do I find c1? I derive f once and plug in a. So you could theorize that c2 is derive f0 twice, and plug in a. So let's see if that's the case. Take this and derive it again. So take the second derivative of f. Now this is going to be 0. This is going to be 2c2, because this is x to the power of 1 here. And then this is going to be 3 times 2, right? The 2 comes down from the power rule. X minus a like so, and then continues. This time when I plug in 0, or a, I keep saying 0, I plug in a, everything else is going to be disappearing, so only this is going to show up. So I'll end up with c2, there's this extra 2 that I need to divide. So c2 will be the second derivative of a divided by 2. So that's not really the case. It's okay to theorize that, but... And then the pattern becomes a little more difficult. What you can see then after this is that if you derive it a third time, this is going to disappear. And this is going to be just 3 times 2 times c3. And then by plugging it in, you get that c3 is the third derivative at the point A divided by 3 times 2. And now, if you're not seeing the pattern, what you can see is that whatever is dividing here is the factorial of n. 0 factorial is 1, so dividing by 0 factorial doesn't change anything. Gotta remember this, right? 0 factorial is 1. 1 factorial is 1, so dividing by 1 factorial doesn't change anything. But 2 factorial is 2, so that's why I have this 2 here. And 3 factorial is 3 times 2, so 6. So that's why I have this division here. This n right here just represents the fact that we're deriving the function n times. So this parentheses n is a way for me to stop writing so many primes. Imagine writing 7 primes and then having to count them every time. So I just write this parentheses n to represent that I'm deriving the function n times, plugging in the point A, which is the center of the power series, and then doing plugging in, or dividing, excuse me, by the n factorial. You know, if you want to know the C4, you can kind of imagine starting with, before I do this example, starting with an x minus a to C4 times x minus a to the power 4, deriving it to get 4C4, x minus a to the power 3, derive again to get 4 times 3, C4, x minus a squared, and then derive again to get 4 times 3 times 2, x minus a, and then derive one more time to just get 4 times 3 times 2. So that is definitely 4 factorial. So this is why this is going on. I forgot the C2 at some point, right? The C4 at some point I dropped it. Here's C4. 4 times 3 times 2. C4 equals f of f fourth derivative at a. So to get the C4, you divide this number, and then the factorial here makes sense. This is a formula that you have to memorize. Understanding is better than memorizing, but it's also important to be able to remember this or to come up with it out of nowhere as quickly. So this series is called the Taylor series. This series that's boxed on the screen is the Taylor series of the function at the point A. This is super convenient. So whenever the function is analytic, then its power series, or its Taylor series equals the function in the interval of convergence. So for all functions that we have, on that list before, finding its Taylor series is the same as finding a power series representation. For other functions that are not analytic, then finding its Taylor series just gives you a series. Doesn't mean that the series will actually add up to what the function is. Yeah. We're not going to be dealing with non-analytic functions in this class very much, just obvious, like the absolute value function, which doesn't even have a derivative for you to calculate the nth derivative of at 0. But besides those basic exceptions, we're not going to be dealing with those much here in this class. Calculus 3 in general. It's also important to know that whenever you get the number a equals 0, so if the base of the series, the center of the series is 0, then you call it the Maclaurin series. I think it's kind of a silly distinction. It has to do with history. You know, Maclaurin was the guy who was famous for working with this type of series. And generally speaking, you work with the series at 0. Right? Generally, this is the most common type of series. But Maclaurin insisted in crediting Taylor. So Maclaurin was a Scottish mathematician, I believe, and Taylor was an English mathematician. So Taylor was English, and Maclaurin was Scottish. So because he worked with them a lot, Maclaurin did, people called those series Maclaurin, but he insisted in crediting Taylor, Brooke Taylor. And so this distinction came about. He said Taylor series, and people said Maclaurin series, and then both names sort of caught on. So if I end up stopping at a certain point instead of adding all points to get to infinity, if I add only just a few, then this will be the Taylor polynomial. So if I just do, the C1, let's say the C0 plus C1 up to the Cn term, not going to infinity, just stopping here, this is the Taylor polynomial. So this is actually a polynomial. I stop at n. And this is just like the linear approximation that we see in calculus 1. We write Tn of x for this. And this is a good approximation for the function most of the time, depending on n. All right, let's see an example of this. I hope the idea was clear. Let's see an example of this. How do I find the Maclaurin series for e to the power x here? Let me scroll this down just a bit so I have a little more space. E to the power x. There's no hope, I have no hope of being able to derive e to the power x and to get something that resembles that geometric series 1 over 1 minus x. I have no hopes of this. So what I'll do instead is note that I need C0, I need C1, C2, C3, and so on. So what will C0 be? That will be f of, again, this is the Maclaurin series, so a equals 0, so f of 0 over 0 factorial. So what's f of 0? It's e to the power 0 over 0 factorial. E to the power 0 is 1. 0 factorial is also 1. So C0 will be 1. Now I need to find C1. For that, I need f prime of 0 over 1 factorial, so 1 derivative. And then what's f prime of x? It's e to the power x again. Or the derivative of e to the power x. So that will be 1 over 1 factorial, right? So I'll say it's e to the power 0 over 1 factorial, which is again 1. How do I find C2? Well, C2 from the formula above is, again, let me move this down a bit. This is going to be the second derivative at 0 divided by 2 factorial. So what's the second derivative? Just take this and derive again. But I get e to the power x one more time. So this is going to be e to the power 0 over 2 factorial. So 1 over 2. You can already see that it doesn't matter how many times I derive e to the power x, I remain having e to the power x. Nothing changes. So this will be e third derivative of f at 0, over 3 factorial. It will be e to the power 0 again over 3 factorial. So it will be 1 over 3 factorial. And this was 1 over 2 factorial. And this was 1 over 1 factorial. And this was 1 over 0 factorial. So nothing more fair, right, than Cn being, or nothing less expected. This is pretty much expected that Cn will be the nth, so this will be 1 over n factorial every time. Taking the nth derivative and plugging in 0 gives me 1 every time. So that means the Taylor series e to the power x will be 1 over n factorial. This is not really the Taylor series. I'm talking the Maclaurin series. So that's at n equals 0, at a equals 0. So we'll fix this name here. And so this is the Maclaurin series. You see that I found the Cn's, and that's what it is. This is a series. The next example is kind of haunting me, but I want to solve for the radius of convergence of this. The problem didn't ask me for it. but I'll do the ratio test. And I'll end up with absolute values like this. And then remember, I need this limit to be less than 1. Yes. By simplifying everything afterwards, I end up with absolute value x over n plus 1. And you see this n factorial is going to flip up here. When I cancel it out, I get n plus 1 left. And this here, after I flip it upside down, it's going to end up here at the bottom. I cancel this out with this, and I end up with a power of 1 here because I subtract the 2 powers. And it doesn't matter what x is as n goes to infinity. Fix an x. Fix x first. Then make n go to infinity. That will be 0. Which is always less than 1, right? Always less than 1. So for any x that I choose, this will converge. So the radius of convergence is infinity. And the interval of convergence is negative infinity to infinity. Which means for any number that I want. Yes. If I need to approximate f, and I'll say we can use its Maclaurin series. So let's say I need to find e to the power 0.2. Well, this is, as I know, 0.2 over n factorial to the power n, right? This is that. If x equals 0.2, n factorial right here. And so I don't need to compute stuff forever. I can just do n equals 0 gives me 1. N equals 1 gives me 0.2 over 1 factorial. N equals 2 gives me 0.2 squared over 2 factorial. And I can stop here if I want, or I can do more if I feel like it's helpful. And this would be using the Taylor polynomial of degree 2, because the 2 here. Yeah. So I hope that makes a little bit of sense, connecting all of the concepts.